Okay, so I want to talk about Rolle's theorem and the mean value theorem. And our leading question will be, must a differentiable function attain its average ROC at a point? And our example is the following. Let's say you leave your house and realize you leave something behind. And this is for a less general case, a more specific case. And then you turn around and come back to your house. So you're driving along the street, you make a U-turn, right? Hopefully safely, and you come back to your house because you realize that you forgot something, right? Must your velocity, vertically speaking, relative to the house, must it be zero at some point? Now, notice when I don't get confused, I don't mean the car's speed. I don't mean, oh yeah, car's going forward at X miles per hour. Must it be zero? In that case, no, because I mean, you can take a U-turn faster than 0 miles per hour. I mean, um, vertical velocity, right? This arrow right here, which is the velocity relative to the start, that's what I mean. Better shown by this line. This is a particle, purple, moving along this line, right? Let's say it's a blue particle moving along the line, and it slows down right here and it turns around. Must it have a velocity of zero at some point? And in this case, yes, and where at the U-turn actually, because we're going up and we're going up and we're going up and we're going. And at this point, we have a positive velocity, right? And right here is where we reach a negative velocity. So probably the velocity is going to be zero at the U-turn, and it's best shown by this position graph. We're going up across until the U-turn, then we're going back toward the house. And when our position is at its maximum, we have a derivative of zero. In fact, at the U-turn, when the distance is at its max, the rate of change is zero. And we know this is true by the derivative of local extremum, since it's a differentiable function. And this actually leads us to the following conclusion. First, though, we do need to talk about the fact that it must have a max, right? Assuming that this function must have a max, right? Which I don't know, maybe it's true, maybe it isn't. We'll see. Must the derivative be zero if the initial, right, output is equal to the final output? I don't know. Well, let's look at it though, right? Must have local or min. So if f is continuous over the closed interval a comma b and differentiable over the open interval a comma b, and f of a is equal to f of b, then there exists a c in the interval such that the derivative of c is equal to zero. Here I outlined, some places where the derivative is zero. It just says there's some place, right? This output at a and this output at b are equal. It's just a somewhere. Maybe, maybe there could be more than one place, but at least one place it's zero. And the proof actually shows us a bit more about where it would be. Proof. If we can show that f attains a max or min on the interval, then we know the derivative is zero there, because, assuming the derivative is real. That would complete our proof, wouldn't it? Right? So let's write it out, okay? So, how are we going to do this? Well, we know that f is continuous over the closed interval a comma b. So, f is continuous over a comma b, but this implies that by the extreme value theorem, f attains a max and a min, right? Isn't that what the extreme value theorem is? And this is crucial, right? Now, of course, we're just going to call this X max and X min for simplicity. But the crucial part is that it does, in fact, attain a max and a min. And now, case one is a trivial case. What if the function is constant? So that happens. So those extrema happen at the bounds, right? A and B. Meaning, what are we saying? That is, X max is equal to A and X min is equal to B, or of course the other way around where X max is B and x min is A, right? It doesn't really matter. So since f of A is equal to f of B, the max is equal to the min, right? Regardless of how we want to write it. Either way, the maximum value has to be equal to the minimum value. The only way if this is constant, right? This function is constant. Therefore, pretty obvious, we can know that there exists a C in this interval, so that the f prime of C is equal to 0 because it's a constant function, it's actually everywhere. So that's trivial case. Case 2, on the other hand, which is not as trivial, but still not too difficult. One of the extrema happen at an interior point, right? Happen at an interior point. Okay, what would happen? Well, by our theorem that we know, by the zero derivative at local extrema theorem, we let C be such an interior point, and it's really quite a simple idea because f prime of C is now 0, and f prime of Z is equal to 0 for C in the interior. And we've completed our proof. Essentially, our first case is that both of them are at the bounds, so it's a constant function, so the derivative is 0 everywhere. Otherwise, it is inevitable that there is a max or a min not at the bounds, and the derivative must be 0 there. That's Rolle's theorem. And we're going to use that to prove the mean value theorem. So here's our actual case. Suppose an express train moves from station A, at rest, right? It's going 0 miles per hour, and it passes through station B. It's an express train. It's not stopping at station B, but we have cameras, and we see that the train's time and position between A and B gives us an average speed of 90 miles per hour. Maybe it took 1 minute, and it took 1 minute to travel between and A and B is, I don't know, like, I don't know exactly how long it would be, but you get what I'm saying, right? The average speed is 90 miles per hour. We determined that. But we know on the tracks that it was going, the maximum speed limit that was ever there was 85 miles per hour. So can we tell the conductor, can we charge them with speeding? Can we say, yes, you have to have been speeding, right? Your average speed was 90 and the maximum speed limit's 85. So were you speeding? Well, what if the conductor argues that this is the average speed? That doesn't mean that at any point they were actually going 90 miles per hour. That's when we show the mean value theorem. And it says that if same conditions as Rolle's theorem, then there exists a C in the interior such that the derivative is equal to the average rate of change. Crucial. Shows up in calculus FRQs more than you can imagine. So let g of x be equal to this large complicated function, you might say, but it's just saying f of b minus f of a times x minus a minus f of x times b minus a. And the real idea for choosing this is because we want f of g of a and g of b to be equal. That way we could just use Rolle's theorem. Now, it is continuous and differentiable because it's a linear combination of two continuous and differentiable functions. And we compute g of a and show that that one's pretty trivial. It's negative, it's a negative f of a times b minus a. And g of b, we do some algebra to expand, and notice these two cancel out. So g of a is equal to g of b. This is exactly what we were looking for because now we can apply Rolle's theorem. So g of a is equal to g of b, and by Rolle's theorem on g of x now, there exists a c such that the derivative of g is 0 at c. And also the other thing is that we want somehow, we're thinking about what function to use. We want the bounds to have the same output. And we want, if the derivative of g is 0, then we want the derivative of f at c to be the average rate of change. And we work it out and we get that that's true. And speaking of calculus FRQs, we get this following problem. A customer at a gas station is pumping gasoline into a gas tank, and the rate of flow is modeled by a differentiable function f, where f of t is measured in gallons per second and t is measured in seconds, etc., etc. And we have a table of values. Must there exist a value of c, this is part B, for 60 less than c less than 120, such that f prime of c is equal to 0, and we have to justify our answer. So key pattern recognition is that whenever we see there exist a value, we where the derivative equals, hey, I don't know, some number, we should probably apply the mean value theorem, right? Whenever we see this type of problem, which will show up a lot, we're probably going to use the mean value theorem. And little tip, the answer is probably yes, unless they specify by the mean value theorem. That's a different case. So must there? So can we show that this function f of t satisfies the mean value theorem? So first, it says it's a differentiable function f. So f being differentiable implies f is continuous over the closed interval 60, 120. And of course, it's differentiable over the open interval. So we know by the mean value theorem, right, there exists a c in 60, 120, such that f prime of c is the average rate of change, which is f of 120 minus f of 60 over 120 minus 60. But wait, 120 and 60, they're both 0.1, so it's just going to be 0. So, yes, there is in the interval. And that is our proof, in fact. We could also use Rolle's theorem because it's specifically talking about 0 and the function that outputs match, and that would also get you the point. But instead of having to memorize more theorems, less is more, and just use the mean value theorem. Hopefully that helped. And in the next video, uh, I'm going to move on to the first derivative test, which is really important for identifying local maximum and minimum.